there isn't any free Wi-Fi here, so this part may not be useful to you if, unless you have paid for the Wi-Fi. But if you have, feel free to follow along. So my name is Ernest Adams. I'm a freelance game design consultant, an author, sort of freelance professor. I live in England and I consult for companies all over the world and also teach at a variety of different academic institutions. And this is a talk about a tool that helps you design game mechanics. And I'm going to demonstrate it here. It's free, so this is not a product pitch. And talk a little bit about what it does and how it works. And I would like to have your involvement in the part of the lecture. So just kind of a general introduction, that's who I am. And I want to start off by talking a little bit about the different kinds of mechanics that there are in video games. Physics, running and jumping and ballistics and vehicle physics and all that sort of thing. Economy, internal economies, collecting things, resource harvesting and so on. RPG skill systems, all those things where values flow around and can be exchanged for other values. Progression, moving on, advancement in some form or another, locking key mechanisms, level and story pacing. Tactical maneuvering, kind of typical war game sorts of things, zones of control, establishing supply lines, team tactics, and that kind of thing. And social interactions, bluffing and making deals with people and coordinating actions and so on. So these are sort of 5 broad categories of game mechanics that we tend to have to work with. And today I'm concentrating almost exclusively on internal economies. Internal economies are complicated and trickier. They can be complicated and tricky to model. And we, until recently, haven't had a good way to visualize an economy. So we have a variety of ways of prototyping as well. And there's paper prototypes, of course, making board games and that kind of thing. The nice thing about paper prototypes is that they're fast and they're cheap. It's very easy to rapidly change the rules. But the difficulty is that they're relatively slow to test and they don't do physics well. It's hard to do a board game about an action video game. So there are certain problems with changing paper over into video games. If you're doing a puzzle game, it probably works pretty well. And it is slow to test. If it's a multiplayer game, you have to gather other people together and so on. So, trade-offs there. Another approach is if you are doing something that involves a lot of numbers, is to build the thing in a spreadsheet. That is moderately slow. It's kind of awkward to use spreadsheets. It's cheap to implement. It doesn't really cost you anything. Again, it's easy to change. But while designers are quite familiar using spreadsheets for keeping track of large quantities of numbers like values of units or attributes of athletes on teams and things like that, actually building simulations inside Microsoft Excel is something that most designers are not that familiar with. Running and tuning a simulation from within Excel. So, again, there are trade-offs there. And finally, software prototyping, of course, is the fastest to test, and it's very direct. Often you can take your software prototype and turn it into the actual software of the game. But of course, it's slow and expensive to implement. A designer typically can't do it by themselves unless they're also a programmer. That means you need to have a programmer to help you with it, and it's slow and it's prone to bugs and so forth. So these are some of the prototyping methods we have. None are particularly ideal, and so that's kind of the background of the situation that I was in when we were in when the co-author of this lecture, his name is Ernest, started working. So I'll explain about who Ernest is and so on in a minute. So mechanics create gameplay. It's kind of a basic principle of all game design. The mechanics are the rules in an algorithmic form, and they determine whether Lara Croft successfully gets across the chasm or not, whether she falls down in. That's the physics mechanics, the physical mechanics determine her success or failure of things, and so on. So mechanics are where gameplay comes from. But when you're trying to describe mechanics, there are a lot of abstract terms and they aren't terribly easy to visualize. I've written a textbook on game design called Fundamentals of Game Design, and you know, it required introducing a bunch of rather specialized terms that are, you know, are not that familiar to the layperson. So there have been a variety of efforts over the years in the game industry to try to systematize mechanics and to create a sort of a uniform way of talking about them and describing them. So Doug Church wrote a very famous article for Gama Sutra called Formal Abstract Design Tools. Noah Falstein and Hal Barwood had a project running for a while called the 400 Project, in which they were trying to create 400 rules for game development, or game design, really, in which certain rules would trump other rules and so on. They were trying to sort of collect up these rules, and I don't know, I think they have maybe 40 or 50 right now. Ralph Koster worked for a while on trying to create a diagramming language called the Grammar of Gameplay. Again, it got complicated fast and it never went too far, I think because he really tried to do too many things at once. And then there's a project called the Game Ontology Project, which is an academic effort in which they're simply trying to record names for things. So when I wrote Fundamentals of Game Design, I introduced certain terms to describe features of an internal economy, in the economy of game. Resources, which are values that change, the things that flow around. Entities are essentially, for those of you who are programmers, they are variables. They are objects which store a value. And then various features of an economy. Sources, which are things that create resources out of nothing. Drains that make them disappear again. Converters are a feature of a game or a feature of an economy that turns a resource into something else. So, you know, you spend a certain amount of money and you get a car. You know, you could be saying to be converting money into a car, or, you know, any other kind of process that turns one thing into another. You know, it takes so much flour and so much water to make a loaf of bread, for example. So a bakery is a converter process. And then traders are processes that exchange things between owners. So you have people that own things on either side, and things get exchanged at a particular rate, and that's a trader process. So these are terms that I introduced. You know, I'm not claiming it's any big deal that I introduced them. It's just the names that I happen to use. And then events, processes, and conditions. Events are, of course, you know, one-off things that occur in a game that cause things to change in the economy. Processes are continuing operations that run until stopped, and conditions are triggers that detect when particular things have occurred. So this is the terminology that I use to describe game mechanics in an introductory textbook for undergraduates and you know, young designers. And what happened here is that a Dutch scholar, well, he was a PhD student at the time, named Joris Normans, read my book, and he thought, you know, it would be really cool if we could create a diagramming language, a visual language that would enable you to actually draw pictures of an internal economy on paper. So he created the Machinations framework, and Machinations is his name for it. And he just, you know, borrowed my terminology and then created this diagramming language. So the various features of the language are nodes, where a node is a game entity or an economic function. Here's a picture of some of the nodes. Sources, drains, converters, and traders. And a pool is essentially an entity. It's a place where resources can pile up. You know, to a programmer, it looks like a variable, but resources can be sort of collected and depleted from a pool. The resources move around from node to node. They pass through nodes, or they stop at nodes and move on, and it kind of indicates the state of the diagram. A resource connection is a solid line that shows where things can move from one place to another. So indicating that a source creates a resource, and then it passes along its resource connection and goes to a pool, for example. And a state connection is a dotted line, a dotted arrow, and it indicates, stuff doesn't pass along it, resources don't pass along it, but it transmits information about the state of a pool. So you can use a state connection to indicate when there's a change in the number of objects in a pool, the number of resources stored in a pool, you can transmit that delta, that change, to something else. And you can use a state connection to trigger things. You can use a state connection to change the behavior of other nodes and so forth. So at the moment, this is all kind of abstract, but I'll be showing it to you in operation in a minute. So he originally began thinking of this as merely a diagramming language for use on paper or in a drawing tool. And then in the process of this, he met another famous French designer named Stéphane Girard, who said, why don't you code this up and make it into a simulation tool that actually lets you do it in real time? And so that's what he did. So the Machinations framework began as a diagramming system, but it turned into actually a tool, and this is it, and this is what it looks like. It's run in Flash. It's available at his website, which I gave at the beginning, and I'll give again at the end. And it's a drag and drop kind of Visio style thing. And can you see my mouse cursor? Yes. Okay. And this isn't just all the kinds of resources that are available here, so or features that are available here. So you click something over here on this, and then you click out here in your main window, and you can draw stuff. So running quickly through the various kinds of things that are available in Machinations, we have a source. This generates resources. A drain makes them go away. Again, a converter that turns them from one to another, at possibly at a ratio. It can turn one thing into two things, or two things into one thing. A trader that exchanges resources between pools. A pool you already know about. A gate is a place that does not store up resources, it simply passes them through, but it's capable of passing them in different directions. So it can send the thing off, to you or you or you, and it can do this in a variety of ways. Gates are actually quite powerful, so it can pass resources along the sort of a round robin way. So first you get the first one, then you get the next one, then you get the next one, and so on round and round. Or it can do it probabilistically, so there's a 35% chance that you'll get one, a 35% chance that you'll get one, and a 30% chance that you will. Or if it doesn't add up to 100%, then there's also a possibility that the resource will be destroyed, that simply disappear. So you can use gates to allocate resources in different directions based on circumstances, either random or other factors. Then if you look at the next row here, these first three items indicate features that enable you to change how a node works. So this source here that's on the first row, the left-hand edge, is a passive source. It won't actually generate a resource until it's triggered somehow. However, you can change what kind of a source it is into an automatic source, and if you do that, it gets a little star beside it, and that means it, by default, automatically generates one resource every second. And you can change that amount, but it doesn't have to be triggered. It just does that right from the beginning of the simulation. Another possibility is you can make it an interactive source. That means it gets a double line, and in that case, it only generates a resource when the user clicks on it while the simulation is running. So you click on an interactive source, and it will generate a resource as the simulation runs. And then a starting source generates the resources once at the beginning of the run and never again. So these are just additional features that you can use to build interesting stuff. Resource connections and state connections I already described. Then there's a bunch of other fancier features that I won't go into in too much detail here because we don't have time, but a delay takes in a resource, holds it for a certain amount of time, and then lets it go. So you can specify how many seconds it will hold on to it before letting it go. A queue will take in a certain number of resources, and when the queue has filled up, then it will start letting them go again one at a time from the end. A passive register is simply a box that can show a number inside, and you can use a state connection to go from a pool to this passive register, and it will show you how many things are in there. An interactive register is another box that you can use while it's running. And by clicking up and down arrows, you can actually insert numbers into your simulation. So you can change quantities by clicking the interactive register. An end condition is a device that detects some state. It's always connected to with a state connection. And when that condition is met, then the simulation stops running. And you can give end conditions different names so you can detect why the simulation stopped running, which end condition it was that stopped the simulation running. So if you have two competing players, for example, you can detect whether player A won or whether player B won. And then finally, an artificial player is a node that contains a little scripting language that enables you to define a strategy for playing your simulated game, such that the artificial player will virtually click a source, or actually any interactive node during the course of play. And you can write scripts that say, well, when the following circumstances occur, click on this. And this lets you, with artificial players, lets you define different strategies of play and then try them out. These different resource connections allow you to put a number beside them that indicates how much stuff will flow through them. So there's a flow rate here by this resource connection that says 5 resources will flow through it at one time. But you can also put a probabilistic number, so a percentage. So this means that every second there's a 35% chance that one resource will flow through, and it simply won't flow through if the die roll doesn't work out that way. Or you can set up an interval, so there will be 2 resources every 5 seconds. And if you put a fractional value like 1.5, that means you're guaranteed 1 resource every second, and then there's a 50% chance that you will get a second one. There's no such thing as a fractional resource. That's important to know. So when you see fractional values, it just means there's a certain probability. The fractional value represents a probability. In state connections, these dotted lines enable you to modify the numbers elsewhere. So this label modifier here says when the pool that this state connection is connected to either goes up or down by 1, transmit that delta to this number on the resource connection. And I'll show you how all this stuff works in a minute. This all seems rather abstract at the moment. There are other kinds of state connections. This one with a star beside it is a trigger. You'll notice this is a passive source. It has no star by it. So it won't generate anything until triggered, but under the right circumstances, something can trigger to cause it to generate a resource. A node modifier will cause the contents of one node to modify the contents of another node. So one pool to modify the contents of another pool automatically. So every time this left-hand pool gets a new resource in it, the right-hand pool automatically gets 2 new resources in it. And finally, an activator is a state connection that has less than or greater than or some other symbol that indicates a condition that turns things on or off. So this on the left here is a pool full of black resources. They pass into this automatic converter, and the converter will turn them into red resources. But when the red pool gets 5 objects in it, it will turn off this automatic converter. So the converter sucks things out of the left hand, turns them into red resources and puts them in the right hand pool. But when the right hand pool fills up, it gets 5 things in, and this activator switches this off. So you can build obviously very complicated and powerful things with this. So does anybody in here actually, does anybody in here actually have this going? Did you follow the instructions at the beginning and go to the website? Any hands? On the internet, it's possible. It's all written in Flash. It's a shockwave file. You can download the shockwave file and load it into a standalone Flash player if you want to. It's Adobe calls it a projector. And I'm running machinations in the standalone Flash projector here. So I'm going to create, we're going to start by clicking here on source and move out here and click, and by default a source is automatic. This pane here on the right hand side under the list of different kinds of nodes indicates kinds of adjustments that you can make to a particular node out there. So this source there's a line here that says activation, and you can indicate passive or interactive or automatic or starting source, and in this case, the default is automatic. We're then going to create a pool, and just click on the pool, the circle, and put it out there, and then we're going to create a resource connection going from one and click on the other one to the next. And then if we click run at the top left-hand side, then once a second, a resource is generated. Very simple, very straightforward. And it will just continue to do that indefinitely. When it gets above 25, it's not reasonable to be looking at little circles anymore and start showing numbers in the pool instead of little dots. So, and then if I want to put a drain, I click the drain node there, and let's make this drain, change the activation mode. So down here in the panel, we'll click interactive, and now it doesn't work until clicked on. And I make another resource connection from there to here, and if we run that, this runs by itself, but once I click here, it will drain a single resource. And finally, I'm going to take a state connection, that's the dotted line, and I'm going to draw from the pool out into the middle of nowhere, so we get a kind of a neat drawing. Out here, and then down here. And that currently says greater than 0, but down here in the state connections panel, I'm going to change this to read, say, less than 10. And what will happen is that the pool will enable the automatic source to generate resources as long as there are less than 10 resources in it. But when there are 10, then it will switch off and stop, as you will see in just a moment. And now the simulation is continuing to run, and in fact, we can see that because I can drain a few things, and it will fill back up until it stops again. And we can, in fact, do one more thing. It's possible to put numbers beside these, so I'm going to, put a number beside this. So it, by clicking on the label box here, now it generates 2 every second instead of 1 every second. You can see it fills up faster. And there's a special label that you can also add, which says all, which will cause everything in there to drain. And it just takes it all out in one go. So I don't know if you've been able to follow along, if those of you who have been building this along with me, it's also possible to put names on things. So I'm going to go ahead and do that. And you probably, most of you have already recognized what this object is. We have just created a toilet. So, it's a nice, neat little self-regulating device that takes in water from the water supply, fills up the cistern. When the cistern is full, it stops, and then when it flushes, it takes all the water out of the cistern and the water supply reruns. Very straightforward, just a little self-regulating object. I can save these not via the file command up here, which is the projectors, and it's for loading shockwave files. But over here at the right under this file thing is load and save. They're saved as .xml files. There are no brains in what it saves. It's important to know this. All the brains are in the shockwave thing. So the XML files, all they do is say where things are and what they're connected up to. So at the moment, there's no mechanism for generating running code that implements this. But you can save it off as a .svg file that is a vector graphics format that enables you to show, turn into pictures that you can show other people or publish and so on. So going back to the lecture then, This has been in development for about 4 years. Yoris started building it quite some time ago, and like I say, it gradually turned from just a diagramming language into a prototyping tool. He's now given quite a number of workshops and papers on it, and has had contributions from academia and industry. And at this point, you're probably wondering, well, why in the hell is Ernest Adams here talking about this, and not Yoris Dormans? What happened was, Yoris and I were both at a game jam on a little island off the coast of Holland, and he brought his laptop to me and he said, I want to show you this thing I made using some of the terminology from your book. And I took one look at this and went, oh my God. I grabbed him by the lapels, metaphorically, and said, you and I must write a book now. So we did. And we took his PhD thesis, and I have publishing contacts because I've written several books, and he had this amazing thing, and we wrote a book called Game Mechanics Advanced Game Design that is a general introduction to game mechanics. Well, it's not an introduction, it's a more advanced look at game mechanics, but it also introduces the Machinations framework in great detail. So if you want to know more about Machinations, it doesn't really have a manual, but the book is as close to a manual as you're going to get. And it describes, how to use Machinations, and there's a lot of commentary about internal economies and so forth. It is meant to be a textbook. It has exercises and stuff in it. So that's how it came to be that I'm involved. It's actually Yoris's tool. It's totally his intellectual property. I don't own it. I'm just its biggest fan. So, and I go around and show it to people because I think it's totally awesome. So what I'm going to try to do now, and this works with varying success, is build a game on the fly. So we will see, and I don't expect anybody to try and follow along with this because it's pretty quick, or I'm going to go pretty quickly. But what I want to do is build a game rapidly from a cheat sheet that I have here, and then solicit suggestions from you in the audience about how we might modify it and improve it kind of on the fly. So I see I'm already very far behind, so I will do this as rapidly as possible. So we're going to create a source that is a mine, and it generates minerals, and it creates minerals 20 every second. And we're going to set up a converter that is an interactive converter, and we're going to say that it takes 10 minerals to build one spaceship. So now if I run this, and I try to click that, nothing will happen because I don't have 10 things in there. Minerals are being wasted. But once we get 10 in there, then I can click this converter, and they'll get drained out and produce one spaceship. And in fact, I can change this so it doesn't waste any. I can change the mode of this converter so that it doesn't waste any. It won't pull minerals out of the pool unless there's enough to pull. And I'll just say, build there. And with these ships, we're going to go explore the galaxy. So, we're going to send out, say, 5 spaceships and explore the galaxy, and we will hope to find planets. So, in effect, when the spaceships go out and explore the galaxy, and they happen to be lucky enough, we'll say that there's a 65% chance that our 5 ships will find a planet. Essentially, the 5 ships will get converted because this is an interactive converter. They will get converted into a planet that we have found, effectively for the purposes of this simulation. But the other thing that we're going to do is create a positive feedback loop. So the nice thing about finding planets is that every time you find a planet, you have a new source of minerals, and you can mine faster. So I've created a state connection that passes along the delta. Well, let's go ahead and label this. Passes along the delta from the number of planets found to the mining operation. And so every mining planet found will increase this number by 1. So if we start running this, we'll wait till we have enough ships, and we'll start building spaceships. And as soon as we have 5, then we'll try and explore it. Now, I've probably set the probability is a little too low. Yes, we found a planet. Okay, and so now this delta has passed along, multiplied the change, whatever the delta was, by 1, and now this is generating 3 at a time instead of 2 at a time. So we now have a positive feedback loop. And Yours' sort of whole point in doing this was to be able to actually see positive feedback loops, so that you could actually literally see the loop there. Because it's all very well when you're trying to talk to undergraduates about positive feedback loops, but if you don't actually see a visible loop on a piece of paper, it's not nearly as obvious. So we'll try exploring some more. Oh, we're not finding anything. There's another planet. And so now it's gone up again to 4. Actually, I should have made this a pull all type node, so it won't explore the place you have 5. Now, okay, so at the moment we don't really have a game because we don't have any decisions to make, right? You just decide to build and you decide to explore, and that's all there is to it. But we can do another thing, which is put in a mechanism whereby we have shipyards. And so we have the option to convert minerals into shipyards. And once again, interactively. And I'm going to change the label on this to read 0 times 10. And that, I'm not doing this very attractively. But shipyards, we're going to say, are fairly expensive. And we're going to change the production rate here from 2 to 20. And so now, when we run it, we're getting 20 every second. And at the moment, we can't build anything because we don't have a shipyard. But once we make a shipyard, we spend 100 of our resources, then that goes down into here. Oops, I've done something wrong. Oh, yes. It should be +1. And there we are. So we can't build yet because there's no shipyard. But as soon as we have enough money to make a shipyard, then we now have the capacity to build ships one at a time rather slowly. And so we now have a decision to make whether we invest in shipyards early on. And now we have 2 shipyards and we can build faster and so forth. And that enables us to start exploring more quickly. So we now have a control mechanism, and we have a decision for the player to make about whether they take a short-term strategy or a long-term strategy. And I'll describe this, that kind of thing more in a minute. So we now have the ability to build shipyards and to build ships and to figure out where we want to spend our money. We could also make an arrangement whereby actually exploring costs, and not only ships, but it costs minerals too if we wanted to, and so forth. So we have this set up. What would you like to add? Yes, sir. Aliens that come and take away planets randomly. Right. That's a great idea. So how about we say, well, if you explore, some of the time you might find an alien planet. You know, does that seem fair? So what we're going to do is we're going to say alien planets. Whoops. And so a certain amount of time you find an alien planet. And let's increase the probability that you'll find a planet somewhat, say 85%. And say that the chance of finding an alien planet is 50%. And then what we need is for these aliens to drain our planets. So we put in a drain, and we put a stake connection from the alien planets to the drain. Sorry, that's not where I meant that to be. So the drain is going to drain our planets. And then this stake connection is going to go from the alien planets to the drain rate. And this is going to be an automatic drain. So, let's see if I've done this right. So we build a shipyard. No, I didn't have enough. There we go. And let's build another shipyard. Now let's start building a bunch of ships and send them out. Okay. We found an alien planet, but it's not draining because I set this value wrong. This should have initially been a 0, and this should not be an all or nothing. It should be a plurality. So, you know, you can see that it's possible to set these. I mean, you told me that, like, 30 seconds ago. And I haven't yet shown it working properly. But you can see, it's possible to prototype these things very rapidly through these kinds of changes. So, now we have risk. And, what the heck? Let's build in fighting the aliens. Let's say that one of the opportunities you can do with your ships is, instead of just exploring them with them, you can actually take those ships, sorry, that's not what I meant, and try draining aliens. We're going to kill aliens. So this is an interactive drain. And we're going to say, well, we can send out 4 ships, say, and when those 4 ships go, then it will drain an alien planet. So now we have a choice to make, another choice to make. Do we explore or do we fight aliens? And you can kind of track this stuff and make decisions about it. Let's see if this actually gets us anywhere. Yes, okay. So the planet we found got drained here because we also found an alien planet, so they took our mining planet. And let's just build a lot of ships in a hurry. And let's kill those darn aliens. So, very, very simple little game. Took kind of, 10 minutes to build and play with, and I can adjust these numbers and change all sorts of probabilities and rebalance the game in a variety of different ways. So back to the lecture. One of the things that Norris did after he started doing this was he began to realize that there are patterns of internal economies that appear in games again and again, and he started building a design pattern library. And design patterns are kind of a buzzword in a lot of fields. In the game industry too, there have been various efforts to sort of document design patterns, more or less successful, but Norris was concentrating purely on these economic patterns. And so he started collecting up a design pattern library, and they are all available both in our book and on the wiki that is at his website. So you can see these, and I'm going to introduce a few of them to you. So one of them is the dynamic engine. This is the classic positive feedback loop engine that we find in so many games. You have a source that produces energy or something valuable of some kind, and you have the choice of draining that off with various actions that are outside the dynamic engine, so you use the energy for something else, or you can invest in upgrades. So you can take the energy from outside, from this pool, convert it into some kind of an investment into an upgrade, and the upgrade, transmits this along to the source production rate. So it just improves the source production rate. And this allows you to create a sort of a trade-off between short-term and long-term play, because the player decides, okay, do I want to use my energy on actions right now, or do I want to invest in upgrades? And the absolutely classic example of this is in StarCraft. Do you build SCVs or do you build troops? Because the more SCVs you build, those constitute upgrades, and it enables you to mine minerals faster and faster and faster. So you get a nice positive feedback loop there, but sooner or later you're going to get attacked. And if you don't have any troops by then, you're going to be in trouble. So you have to decide which is the appropriate way to do it. So this tends to favor players who invest the most, and I'll show you an example in a second. And then, the long-term strategy is dominant, provided the other guy is not doing a tank rush. If he's doing a rush, then you better choose the short-term strategy. So, one of the things you can do with this, which I didn't show you, is you can track things by putting in graphs. So, very quickly, one of the things you can do is draw a chart and use a state connection from the pool to show the contents of that. And oops. And now you can see that it's tracking the number of ships that are available for use. And as we build more ships, the chart is tracking. So you can track many different things at one time. You can change the colors. You can export the values to a comma-separated value for a file for later analysis in Excel and so forth. So it's a very useful data analysis tool. Another thing that you can do is do a quick run, which turns off all these nice, pretty graphics and just does a very rapid, high-speed run until it stops for some reason, if you have an end condition in there. Or you can do multiple runs. So you can try, running this. This has some probabilistic stuff in it, so not every 2 runs is necessarily going to be alike. You can do multiple runs and say, do 1,000 runs in 20 seconds, and then compare the results of different kinds of strategies. So that's a very useful thing. So here's a very good example. When you invest right away in upgrades, then you have very little energy initially at the beginning because it's all going into the upgrades, so your energy line is flat and the number of upgrades is going up. Then you stop investing in upgrades and you start building, and now you're building at a pretty rapid rate. And this compares the long-term and the short-term strategy. So the short-term players, the blue player, they stopped investing in upgrades earlier, and so they started getting whatever their energy was pretty quickly, but they get it at a slower growth rate. This is just a nice illustration of the trade-off. And we could in fact make a machinations diagram that automatically diagrams this very easily. Here's another pattern. This is attrition. It's just players are stealing or destroying each other's resources somehow. So you have a certain amount of strength in a pool. and you drain your own strength in an attack, but that also triggers a drain on the other side that drains the other player's strength. And they likewise do the same to you. And this is just the attrition pattern. Escalating challenge, you want to make things that get harder and harder. So if you look at this right hand, these are two different ways of implementing the same thing. If you look at the right hand one, this is a gate that doesn't actually gate anything, it's just interactive. When you click it, it triggers a source that generates something that represents progress. So, but there's only a certain probability, it says N% here. There's only a certain probability that it will be successful. So you click this, and depending on depending on the probability, you will generate some sort of progress. But as the progress goes up, this state connection, you notice there's a minus sign here, transmits this delta as in lowering the percentage. So the percentage that you're clicking this will be successful in generating progress goes down as progress goes on. So it's effectively, it's a little tool for just making things harder. The farther along you are, the harder things get. So these are the general categories of things. I've just introduced you two. A static engine just is a source that generates something at a fixed or an unpredictable rate. Every time you pass go, you get $200 in Monopoly. A dynamic engine has the ability to invest in upgrades, so you can have that positive feedback loop. A converter engine has two things that are going around converting things from one to another and creating a surplus along the way. Engine building is a kind of gameplay where it's really all about setting up these engines in the game and making them successful. So all the sorts of management games like SimCity and so on are about setting up an engine and making it productive. Friction is the opposite, it takes things away. Static friction is a drain that automatically consumes resources, either at a fixed rate, it's time to pay the rent, or perhaps at a random rate. It's like the chance and community chest cards in Monopoly, where suddenly you have to pay some money. Dynamic friction is governed by other elements. So the amount of rent that you have to pay is based on the number of properties that are on the or the number of houses that are on the property and so on. So it varies depending on other features inside the economy. A stopping mechanism or a law of diminishing returns is something that causes a mechanism to be less effective every time you use it. So the player says, "Oh, this is awesome," and they use some weapon or something, but the next time they use it, it's not quite as effective, and it just keeps going down and down every time they use it. This is, again, a common feature in video games where you don't want the player to get too excited about one thing. And attrition, I've already showed you. Escalating challenges, we talked about that. And then one of the points of all of this is that Ernest and I are both very interested in trying to create game experiences that don't depend on scripted events. An awful lot of war games and stuff like that have scripts in them that say at exactly 30 seconds or 30 minutes or whatever, this event will happen. And every time you play that level, that scripted event always occurs because it's just fixed. Well, we're interested in learning how to create more flexible kinds of games that have emergent properties. So you have this kind of dynamic stuff that is going on instead of just having fixed scripted events. Escalating complexity, things just get more and more complicated, not more difficult, but more complicated. Tetris is a good example. And an arms race where you're trying to build stuff as fast as possible against other people. And then it's got a miscellaneous collection. Playing style reinforcement. RPG character classes are a good example of this. Essentially, if you choose to be a mage, then if you play like a mage is supposed to play, your playing style will be reinforced and you will do well. However, if you start playing a mage as if they're a warrior, that behavior is not reinforced. And so you can set up your economy in such a way that it rewards particular sorts of choices. Multiple feedback systems, you can set up more than one feedback loop. In Ernest's experimentations, he found that, generally speaking, 4 is about the maximum for any game. Beyond 4 feedback loops, it begins to get too complicated for the player to understand, and typically, the less important ones become irrelevant and the player ignores them. You know, typically there's a couple of feedback loops that are really dominant in the game, and others are less important. So, you know, there's not that much point in going beyond about 4. Trading systems, of course, and worker placement, it involves allocating limited resources to a production task. So you've got a certain number of builders, and you have to decide where you're going to put them to build different kinds of things. And that's, you know, a very common gameplay decision that we give people, and you can construct that pattern in Machinations and Illustrator. And finally, a slow cycle is just a pattern for indicating things like the change of the seasons. So, you know, winter to summer or night to day, you have a slow fluctuating cycle that changes conditions, and that, you know, generates interest for the player and means that, you know, sometimes they might decide, okay, it's now my time. This is the best time to attack or to grow crops or whatever it is, and so, you know, they will do it at that time and not at some other time. And, you know, initially when they're newbies, it may take them a while to figure out which part of the slow cycle is the most efficient. We want to emphasize that there isn't a silver bullet here. I don't want to oversell this thing. I personally think it's awesomely unimaginably cool, but it is a prototyping tool. It is designed to explore game economies. You know, it will not build your game for you by any means. You know, it lets you try stuff out, figure out what works, balance it a little bit. And the nice thing about it is it enables you to make balancing decisions very rapidly. But it's, you know, there are certain things it doesn't do. It's good for kind of a general structure of an entire game. You can build kind of a very broad scale structure and not do the small details. Or you can do a small detail, you know, say, well, let's simulate cities in Civilization, but only cities and nothing else, and take a close look at something. What you don't want to try to do in Machination is build the whole of Civilization in, you know, the one thing, because it, you know, it's good for the broad scale look or the close in look, but not both at the same time. So it's still in development. Some of the future features that we're thinking of including multi-page diagrams. At the moment, there's only one page. Hierarchical design and being able to user-defined nodes. I think this is really important. To be able to build a little mechanism and then say, here are its inputs and outputs on the edge of the page, then fold it all into a box and use that box mechanism at a higher level in the hierarchy. That would be very useful. And at the moment, like I say, it's written in Flash, and you need the Flash player, and it would be nice to have a standalone application or a mobile app. And also to be able to integrate it right into engine architecture. So to be able to generate source code or something else that runs through that. So this is where you can find out more about it. If you're interested, jorisgormans.nl/machinations is where it all is. As I say, it's all free. You can't download the source code. It's not open source, but you can download the Shockwave file. There's a wiki that is full of tons of examples. You can see the wiki there, Machination/wiki. And then our book is available at PeachPit. That's our publisher, peachpit.com/gamemechanics. And the fact that other people are sneaking in the back suggests that I have run over my time. So that is the end. And thank you very much for your time and attention. Should I? Okay, so they're waiting for the room. In that case, I'm sorry to say there's no time for questions. However, I will be the fat guy with the green hat. And if you find me outside, you're welcome to talk to me about this as long as you want. Thank you all again, and I will get out of the way now.